Let us now take a look at some techniques of integration. So what methods can we do to calculate the integral if the integral is not in the list of basic integrals? The first technique, which we already briefly explained, is the technique of substitution. Let's introduce this technique through an example. So suppose we have the integral of 2x times the root of 1 plus x squared dx. We want to find this integral. This integral is not in our table, and the main issue here is the 1 plus x squared. So this makes it more difficult to calculate the integral, and so we have to work around it. So we have to find a way to work with this 1 plus x squared. So you could say that the root of 1 plus x squared is actually a function f of another function g of x. So f being the root function, g of x 1 plus x squared. What we will do to solve this is to introduce a new variable. So a new variable which will help us simplify the expression. Let's say this, or let's call this new variable u, and say u is equal to 1 plus x squared. In the expression of the integral we also have a dx, so we have the differential of x. And if we then change to a new variable, we also need to find the differential to this new variable. So what we can do is we can look at the derivative du dx. So we derive u to x, and this is equal to 2x. And so we can write that d of u is 2x dx. Then we move back to the integral. So the integral of 2x times the root of 1 plus x squared dx. And we will use this new variable. We will replace the x variable by the u variable. So if we replace this, we get an integral of the root of u. And then we see that 2x dx, this is the same as du. This is a very simple integral. So it's the integral of u to the power 1/2, which is 2 over 3 times u to the power 3 over 2 plus a constant. And then since we have an integral in x, we have to transform it also back. So 2 over 3, u is 1 plus x squared to the power 3 over 2 plus a constant. So if we want to write substitution in general, what we have is we have an integral where we have a function f of g of x times g prime of x dx. So we must have something of the form f of g of x and then also the derivative of g of x. Why do we need this? Because in this case, the substitution that we will be doing is we set u equal to g of x. This means that d of u is g prime of x dx because we take the derivative. And then this one becomes f of u, and this part together is equal to d of u. So this integral after substitution becomes the integral f of u du, and then in such a way that this new integral is more easy to calculate than the old version of the integral. Let's make two remarks with substitution. First remark, if we have a definite integral, then we also have limits of integration. So a definite integral gives me limits of integration in x, so it means you also have to adjust those limits of integration to u. So we need to recalculate the limits of integration from the old variable x to the new variable u. And then the second remark, you have to always write your final solution back in the original variable. So you substitute u, you get a solution in u, and then you have to replace u again as being a function of x, so that your final answer is a function of x. To illustrate this method, we will make some examples. So for the first one, suppose we have an integral of f of a of x dx. We want to calculate this integral. The obvious substitution would be that you say u is equal to a of x. So this means that du dx is a, and so du is a times dx. If we then plug this in, this is the integral of f of u times dx. dx is du divided by a, which is 1 over a times the integral of f of u du. So we see that if we have a of x here, so we have a function of a of x, the integral gets a constant 1 over a outside. So if we multiply x with a, the integral will have a factor 1 over a. Second example, suppose we have to calculate the integral of x to the power 3 cosine of x to the power 4 plus 2 dx. To substitute, we will look at what's inside my function. So I have a function which is the cosine, and then inside I have another function of x. So I will say that t, after all, is just a name for a variable. So my substitution is t is equal to x to the power 4 plus 2, which is handy because here I have an x to the power 3. So when I then calculate dt, we get that dt is 4x to the power 3 times dx. And I substitute, so I get the integral of the cosine of t, and then x to the power 3 dx is dt divided by 4. This integral gives me 1 over 4. The integral of the cosine is a sine, so this is the sine of t plus a constant. And then I have to transform it back to x, so it's 1 over 4 times the sine of t, where t is equal to x to the power 4 plus 2 plus my constant. So example 3, let's calculate the integral of the root of 1 plus x squared times x to the power 5 dx. For a substitution, we will try the part which is below the root, so it's the function of x within another function, so 1 plus x squared. This means that du is 2 times x dx. So if we plug this in, this is the integral, the root of u. Then we have x dx, so this is x to the power 4 times x. So x dx is du divided by 2 times x to the power 4. So we also need to replace x to the power 4 by an expression of u. So we know that u is 1 plus x squared. So this also means that x squared is u minus 1, or x to the power 4 is u minus 1 squared. And the integral then becomes 1/2 times the integral root of u times u minus 1 squared du. One remark, a very important remark, I wrote this in red because you can never write this as a solution. So it's never allowed to have a combination of u and x in the same integral. This doesn't make sense. This is mathematically impossible. The only reason I wrote this is to show you where it comes from or how the transformation is done. But if you have to solve such an exercise, you can never write a line where you combine the new variable with the old variable. So you have to do the complete substitution at once. And then the rest of the solution is straightforward. So this is u to the power 1/2 times u squared minus 2u plus 1 du. You put them together, so this is u to the power 5 over 2 minus 2u to the power 3 over 2 plus u to the power 1/2 du. And then this is a basic integral, it's u to some power, so you can immediately solve it. And then in the final step, you replace u again with 1 plus x squared. So this is 1 over 7, 1 plus x squared to the power 7 over 2, minus 2 over 5, 1 plus x squared to the power 5 over 2, plus 1 over 3, 1 plus x squared to the power 3 over 2, plus a constant. For the fourth example, let's calculate the integral of sine of 3 times ln x divided by x. Again, substitution, you take the part within the function sine, so set u equal to 3 ln x. This means that du is 3 times dx divided by x. And if I then replace this in my integral, it is the integral sine of u times du over 3. So 1 over 3, the integral of sine is minus cosine. So minus cosine of u plus a constant. And then we replace u again by 3 ln x. So it's minus 1 over 3 cosine of 3 ln x plus a constant. And then for the final example, calculate the integral of dx divided by x squared plus 4x plus 5. For this one, the substitution is less clear, but if we look back at the list of formulas, we know the integral of dx over x squared plus 1. So maybe we can try something like that. So what we have here is x squared plus 4x plus 5. And you see that this is actually x plus 2 squared plus 1. So x plus 2 squared is x squared plus 4x plus 4, and then plus 1. The substitution that we will be doing is set t equal to x plus 2. This means that dt is dx. And I just get the integral of du over u squared plus 1. The integral of this is the inverse tangent. So tangent minus 1 of u plus a constant, or the inverse tangent of x plus 2 plus your constant.